Hello again, Mark Kachmarek. You know my name. It's not deja vu. You're not in a different time continuum. As I warned you, you get me twice today. So instead of talking about today's products, I want to talk about where Intel is going, leading the evolution of compute. We are one of the unique companies that still does fundamental research in two major areas: component level research, as well as how do we put systems together, and that means hardware and software. So as I said, we still do fundamental research. As I said, component research is where we really make use of enabling Moore's Law going forward, developing new ways of integrating solutions into silicon. And then also on our Intel Lab side, we look for new architectural approaches, new systems, and new ways of compute. We also do quite a bit of work with universities funding other research, not only used by Intel, but by the industry as a whole. So I think most of you are well familiar with Moore's Law. The number of transistors and resistors on a chip doubles approximately every 24 months. And to steal a quote from Mark Twain, the reports of Moore's Law's death are greatly exaggerated. For Moore's Law does live at Intel. And I want to tell you about what we're doing to continue the advancement of scaling. For 50 years, we've been on a scaling trend. That early trend was identified by Gordon Moore, and we continue to work on maintaining that trend. So this is a little bit of the history, just recent history. So 90 nanometers, we're approaching 10 now. 90 really wasn't that far ago. We first started working on strained silicon to make the advance into 90 nanometer. Intel's had a piece in every one of these, pioneering most of these efforts. High K gates to get us to 45 nanometer, self-aligning vias at 32 nanometers, FinFETs for 22 nanometer, most recently hyperscaling to get us to 14 nanometer, and a new type of hyperscaling that allows us to now get to 10 nanometer. So innovations in materials and structures have enabled us to continue to scale the transistor. This shows you some of the examples of our 10 nanometer process. The 34 nanometer FinFET pitch combined with a 54 nanometer gate pitch. And then it shows you our metallization activities. Aggressive pitch scaling has helped improve transistor density. And what does that trend look like? So if you look at what we've done over time, so from 45 nanometer, most recent history, to 10, you can see each one of the jumps in density, all around 2.3 to 2.5 times transistor density each node shift. And how does that look? Well, that looks like every 2 years we are doubling the transistor density. I know many people have been talking about 10 nanometer and 14 nanometer. They are challenging node transitions, but if you look at the aggressive steps we are taking in each one of our next process technology steps, we are able to overcome the challenges and maintain Moore's Law. And what does that deliver? Well, if you look at Intel's 10 and 14 nanometer processes compared to others in the industry, we get greater scaling. That means you have a smaller chip, and in fact, we never really create a smaller chip. We add more functionality every time, increasing the performance and power delivered to our customers with each generation. And so what does that mean going forward? Well, going forward, we're all looking at integration. There is 2D integration, which we call SoCs, and then system-on-chip integration, and then also 3D integration, where we're looking at stacking different technology into the same product. And of course, we do have to look beyond CMOS. I know we've been working in CMOS for many, many years. Spintronics is one of the latest areas we are looking at. This is where we are doing fundamental research, but also working with universities and other research facilities on where we're going to keep going on Moore's Law. So that's what we're doing in component research, so you can understand why Moore's Law is maintained and how important it is to us going forward. But we're also doing some fundamental research in our labs. One of those is neuromorphic computing, where we're looking at mimicking the different neuron pathways and synapses within the brain into a chip. So the human brain is quite a bit different than a computer, right? Human brain runs at less than 100 hertz. That's right, 100. Not 100K, not 100 meg, 100. Pretty amazing. That's pretty slow. It's asynchronous. It works in a very noisy environment, and it's highly fault tolerant. It also has memory and compute tightly integrated. And we don't program the brain. The brain learns from event-driven events in the environment. So what are we going to, what are the different learning environments that we all are involved in? Well, there's unsupervised learning. We all know about these. Pattern detection, where we just sit around and our brain naturally enables us to detect different patterns in the environment. There's supervised learning. Many of you, if you have kids, you have done this. You've shown them, this is a plane, and you tell them, it's a plane. So you label the things. And we always have cats. I don't understand that. Always have cats. No dogs. We have self-supervised learning. Again, if you've ever watched your children, if you've had children, like pouring a glass of water, they'll pour it over and over and over again. And most of it never goes in the glass. But eventually they start getting and learning that through that pattern. And then there's reinforced learning for decision making. Something my son lacks, he gets consequences. It never reinforces a pattern, unfortunately. And this leads us to a groundbreaking research test chip that we have provided called Loihi. And it's Hawaiian, named after a volcano, which may become the next Hawaiian island. Why we named it after Loihi? I don't know. I have no clue. Loihi, it is a neuromorphic chip. It is asynchronous, spike-driven. It's got a neuromorphic mesh. This product also is event-driven, auto-correcting, so it can be self-learning. This is a revolutionary new chip. This is not a product. Like I said, this is not a product. This is fundamental research where we're looking at how do you create an autonomous self-learning system which learns from its environment. Quantum computing. I am not a quantum computing expert. However, we do have one in the audience. I'll give a shout out to Jim Held. He's an Intel, one of our great scientists. He'll be talking tomorrow about quantum computing. So I'm not going to steal his thunder or talk anything cool. I'm just going to talk about a little bit about quantum computing. And from the standpoint, it's a new application space we are looking at. People are very excited about quantum computing because of the fact that as problem sizes grow, the resource intensity does not grow linearly with the problem size, which means you can tackle even greater problems at a much more efficient solution point. Right now, we're all working towards, say, the 50 qubits proof of concept area. There's the 1,000, which we think will be able to work on small problems. And of course, the 1 million qubit, that's when you have a real commercial system that you can make use of. And then quantum computing, as I talked about before, it takes an entire stack. It's not just hardware. There is software. And there are applications all needed to create a quantum computer, and Intel is involved in every one of these elements. That gives you a little taste of where Intel is going and where we have more work on the quantum computing front. We are developing chips, and you can see some of the wafers we have in production. As I said, Jim will give you more information on quantum computing tomorrow. So I would say the future is very bright. Intel is working hard to create a greater future, greater performance and capabilities for all our customers. Thank you, and questions? Or applause and then questions.